Hi everyone, this is an NCNGT2021 talk. I'm Fan Ye, and my title of the talk is The Dimension Bounds on Suture Instanton Homology. And this is joint work with Baldwin and Zhenkun Li. So at first, let's have a sketch for the talk. For a balanced suture manifold M gamma, one can define many suture floor homology. Say, for example, suture Heegaard floor homology, SFH. This is a Z module or an F2 vector space, and the chain complex is denoted by SFC. And also suture monopole floor homology, SHM. This is a Z module or a module over lambda, which is a Novikov ring over Z2. And also suture instanton homology, SHI. This is a C vector space. So in this talk, I will say, I will prove that the dimension of SHI is less or equal to the dimension of SFC, the chain complex. And also, I prove that the Euler characteristic of SHI is equal to the Euler characteristic of SFH. So also we can prove similar results for SHI. So this is the main part of this this talk. So in the first part of the talk, I will describe the construction of SFH, SHM, and SHI, and then states the main theorem. And in the second part of this talk, I will talk about the motivation and state the main theorem again, and then sketch the proofs. Okay, so let's start with the construction of SFH. So at first, let's review the definition of a balanced suture diagram. So a balanced suture diagram M gamma consists of a compact-oriented three-manifold M with non-empty boundary. So there's a closed one-manifold gamma on the boundary of M, which satisfies the following condition. So the first thing is this manifold gamma divide the boundary of M into two parts, R plus and R minus. And so by the way, there are different orientations on R plus and R minus. And there's an important condition such that the Euler characteristic of R plus and R minus should be the same. So maybe let's just focus on some specific examples of suture manifolds. So at first, say if we consider a B3, then the boundary of B3 is just S2. So if we choose a simple closed curve on S2, then we will get balanced suture manifold because now the boundary is divided into two disks and they have the same Euler characteristic. Also, we can consider a closed ring manifold, and we remove a ball inside the closed ring manifold, and still we just put a simple closed curve on the ball, and then we also get a balanced suture manifold. Also, say for a knot in a three manifold Y, we can remove the neighborhood of the knot and then add two meridians on the boundary. So in this case, we also get a balanced suture manifold because we know now R plus and R minus are just annulus and they have the same Euler characteristic. Okay, so then let's go to the definition of suture floor homology. So for suture floor homology, we at first need a balance diagram. So the balance diagram is introduced by Juhász, and it is a tuple satisfy the following conditions. So sigma is a compact-oriented surface with boundary, and alpha is just usual curves such that it forms kind of a Heegaard diagram. So maybe let's see. So from the balance diagram, we can construct our original balanced suture diagram. So at first, let's consider sigma times I. and set the suture to be sigma times 0. And then we attach some alpha handles along the surface, and we also attach some beta handles along the surface. So here we have alpha handles. Here we have beta handles. So, so in this case, we can find that all these parts is the boundary of M, and the suture is on the boundary of M, and the inside is just the interior of M. So this is a construction of a suture manifold just from a balance diagram. So if we can construct the manifold by this diagram, we say the diagram is compatible with the suture diagram, with the suture manifold. Okay, so then from a balanced suture diagram, we can define the suture flow homology. So just as usual, in Heegaard flow theory, we choose the symmetric product sigma n of sim n of sigma, which is the product of sigma modulo the symmetric group. And here we use n folds. Also, we choose two tori, which is the products of alpha curves and beta curves. So in this case, we can say this is a symplectic manifold, and those two are Lagrangians. So then we can just define the suture flow homology as the usual Lagrangian flow homology of these Lagrangians. So in particular, the chain complex SFC is generated by intersection points x such that x is the x1 times xn, and xi is in alpha I, but also in beta sigma I. So where sigma is an element in Sn. Okay. So yeah, so roughly speaking, this is the definition is just Lagrangian flow homology of T alpha and T beta. And Juhász proved that for a balanced suture diagram, different choices of the balanced diagram induce isomorphic Z module SFH. So we denote this Z module as SFH of M gamma. So there's a remark that about naturality. So Juhász, Thurston, Zemke proved that the naturality of SFH M gamma, which means it is not just an isomorphism class. It is a real Z module, or but here the proof is only for an F2 coefficient. So it is a real F2 vector space. So then we can say some subspace of this vector space. So we will not use the naturality things, we just mentioned it, and say because everything we consider is just about the rank, so or dimension. So the isomorphism class is enough. So by the way, if we consider the special case we mentioned before, so if we consider y minus b3 and there's a curve on b3, then we just recover HF hat of y. And maybe if we consider SFH y minus the interior of neighborhood of k and put two meridians suture, then we recover HFK hat of y and k. Okay, then moreover, the suture flow homology admits spin C decomposition. So spin C decomposition, roughly speaking, is just a decomposition over H upper 2 and real boundary, or by Poincare duality, it's just H lower 1 of M. Now we denote it by H prime. So so the decomposition means the vector space or the Z module can be decomposed into a direct sum of this subgroup or subspace. So there is also a relative Z2 grading on SFH. So and then we can define the Euler characteristic. So this is not the usual Euler characteristic. It's defined by both gradings. So it is indeed a graded Euler characteristic. Roughly speaking. So so in this case, the definition is that we at first choose the group in some specific spin C structure, and we take the Euler characteristic, and we add an element H, where H is just S minus S0. This is an element in homology group, and by Poincare duality, it is also an element in H prime. So by this way, if we sum all these elements, then we will get element in the group ring of H prime. So note that because the spin C structures is only an affine space over homology groups, then we should modulo some element in H prime, and also maybe modulo plus and minus sign, because the Z2 grading is only relative. Okay, so there's a good theorem for this Euler characteristic, such that suppose H is just the homology group we mentioned before, then the characteristic is just the derived torsion, or kind of derived torsion for the Suture manifold, and in this group ring modulo plus minus H prime. So here tau of M gamma is the derived type torsion and can be calculated by Fox calculus. So later we will just consider the image of this Euler characteristic into this group ring. So note that this group ring is based on homology group H, and H is that we modulo the torsions in these homology groups. So which means this is roughly speaking just some T1, T2, and T3, and something like this. And we can just consider this is as an element of maybe polynomial in T1, T2, T3. Yes. So this makes things easier. Then let's go to the constructions of SHM and SHI. So suppose so maybe let's at first review some basic things for monopole theory and instanton theory. And here in this talk, I will not use any technical details of the monopole and instanton theory, but just just use them as some big black box. So suppose Y is a closed ring manifold. So based on Seiberg-Witten equations, Kronheimer-Mrowka constructs three versions of monopole flow homology, which is HM from, HM to, and HM bar. So they also admit spin C decomposition over Y. So we can also consider the decomposition just as a affine decomposition over H1 of Y. So for any spin C structure with the first Chen class non-torsion, Kronheimer-Mrowka showed that HM bar is 0, and those two groups are just isomorphic. So there is indeed just one essential group, and we only need to consider it as HM. There's no bar and no from, no to version. So for a closed surface R in Y with genus larger than 2, we can define HM YR as the following. So we just collect the spin C structures that evaluates as 2G minus 2 on the surface R, and we just put all things together. So remember, note that in this case, because R is larger than 2, then those spin C structures are always non-torsion. So we can just apply these facts. And finally, we can also take HM from here. So they define the same thing. Also for instanton theory, the basic setup is that Y is a closed ring manifold and omega is a Hermitian line bundle such that C1 of omega had odd pairing with some integer homology class. Well, this is just some admissible condition. And based on Yang-Mills equations, which counts some SO3 connections on some principal bundles, Floer construct a well-defined instanton flow homology. So we call it I omega of Y. So in this case, for any homology class in homology group of Y, we can define an action mu of H I omega of Y. So in particular, for a base point, for a point and a closed surface R in Y, there's an action mu point and mu R, and which commute with each other. So now we define similarly the notation I omega Y R as the simultaneous generalized eigenspace of mu point and mu R, and the eigenvalues is just for the mu point it is 2, for the mu R it is 2g minus 2, which means it is indeed the top eigenspace for this action. Okay, then once we have a definition for HM of YR and also I omega of YR, we can construct SHM and SHI. So the definition is of closure comes from Kronheimer-Mrowka, and they said suppose M gamma is a balanced suture manifold, then we can take accelerate surface T as a connected compact surface such that the boundary of T, the number of boundary of T is the same as the number of components of gamma. Then we can take some pre-closure M tilde such that we glue I times T to M. So maybe we can draw a diagram, say, so remember this is our original suture manifold, balanced suture manifold M, and then we take a surface T, it may have many genus, and we product it with I like this, and then we just glue them together to form a pre-closure. So this is T times -1. Okay, then where's R plus and R minus? So this is R plus, this is R minus, and so this part is R plus tilde, and this part is R minus tilde. And then we just choose a diffeomorphism of R plus tilde to R minus tilde such that we glue them together. We glue this piece together. We glue the piece together, and then we form a closed ring manifold Y. And then we say R is just the image of R plus tilde and R minus tilde in Y. The pair YR is called the closure of M gamma, and the genus of R is called the genus of the closure. Yes, so maybe we can copy the diagram here so that maybe it's more clear here. Finally, we get a closed ring manifold Y with some with some R inside it. Yes. Then we can apply the definition before, say for YR a closure of M gamma such that the GR is larger than 2. And then we define SHM as HM of YR. And also in the construction here, we can choose a base point, say a base point P on the accelerated surface T. And we consider P times I in the accelerated surface times I. And then we choose the edge such that edge sends this point to this point. And finally, we get omega. We say the omega as a closed one manifold in this manifold. So we can say, roughly speaking, this is omega. Yeah. So then omega has an odd pairing with the surface R, which is because the intersection point is just 1, and we can use it to define instanton flow homology. So in this case, we have a closure Y, R, and omega, and the condition is that we just need GR to be larger or equal to 1, and we define SHI of M gamma to be I omega YR. So that's the definition of SHM and SHI. Okay, so Kronheimer-Mrowka proved that the isomorphism classes of SHM and SHI are independent of the choice of the surface, accelerated surface, and also the diffeomorphism edge, and also the point P. And then Baldwin and Zhenkun proved that the neutrality of SHM and SHI. This is just well, the idea is just basically from Kronheimer-Mrowka, and but now we have a real vector space or just projective transitive system, rather than just isomorphism class. So a remark that if we take the closed 3 manifold and minus 3 ball, then we may recover the Tutor version. Well, the Tutor version is defined in monopole flow homology, and also if we use SHI, we would get I sharp of Y, and I sharp is also defined in instanton series. But here I will not say anything about the definitions. So for knots, we can define KHI, which is monopole knot flow homology, as the setup we used before. So we take the neighborhood of the knots and remove it, and add 2 meridian on the boundary. Then we take this as a balanced suture manifold and just apply the construction before. We get KHI and also KHI. So yeah, so those are similar thing for knots in gauge series. Okay, then let's think about also the Euler characteristic or gradings on this SHM and SHI. So at first we need to choose a basis S1 to Sn in H lower to real boundary, and then Zhenkun Li and Zhenkun Li construct Zn grading on SHM and SHI. So suppose that rho 1 to rho n are the dual basis of S1 to Sn. Then we can define chi of the graded Euler characteristic of SHI to be the following. So at first we take the group in this specific grading, and we take chi, and then we multiply it by the dual basis, and then we sum them up. So this is a well-defined element in the group ring of ZH. So remember that H is the H1 modulo torsions, which is also H upper 2M real boundary modulo torsions. So and it's also well-defined just up to an element in H and up to sign. So we can also define chi of SHI similarly. Yes. So this is the definition for chi. And then we are going to state our main theorem. So the first theorem is suppose M gamma is a balanced suture manifold and H is a balanced diagram of M gamma. So there's some admissible condition for H, but the admissible condition is contained in the definition of Suture Heegaard floor theory. So we just choose a good diagram. And then we have the dimension of SHI is less or equal to the dimension of the Chen complex. So remember that the Chen complex is generated by intersection points of X in T alpha intersect T beta. And yeah, it's generated by the intersection points of T alpha and T beta. And we can just describe the generator explicitly and just count the dimension. And also, suppose M gamma is a balanced suture manifold and H is the homology group modulo torsion, then we prove that the Euler characteristic of SHI is the same as Euler characteristic of SFH, but in the group ring. And so there's a remark that we also going to prove theorem. We already proved the theorem A for 1-1 diagrams of knots in length space, and but then we generalize it to a general case. So also there's a work in preparation, which is theorem B can be proved for H prime, which means we can consider the Euler characteristic without modular torsions. So this is a work in preparation. So that's the main theorem, and this is the first part of this talk. So I'll say more things in the second part of the talk. Thank you.